When we talk about graphing the absolute value function, we can talk about translations, reflections, stretching, compressing. Here is the standard form for the absolute value of the function. We have things going on inside the absolute value marks. That is where our independent variable is going to show up. We can see there's our independent variable. They're calling it x. It can be horizontally translated. It can be horizontally stretched or compressed depending on the value of b. Here, outside of the mathematical operation that's happening on the horizontal variable or on the independent variable, we can have a vertical change. If k is positive, that graph's going to be picked up and moved up in the plane. If k is negative, the graph's going to be picked up and moved down in the plane. A affects everything that's after it before the plus or minus sign. So this winds up being a stretching or a compressing vertically. It is a vertical stretch or compress. When A is positive, the graph is going to open up. When A is negative, the graph is going to open down because a negative in front of that function reflects it over the x-axis, just as it has for other functions. So all the translations, reflections, all those kinds of things that we learned about, all of the other functions are true for absolute value as well. I know that this function is one of the parent functions that we have already discussed, but we didn't talk about it in a whole lot of depth. I want you to understand that if you are uncomfortable with piecewise defined functions, you've been working with a piecewise defined function for a long time already. Here's the definition of absolute value. Absolute value is a piecewise defined function. Piecewise defined means that the pieces have unique behaviors over a domain set of values. So from negative to positive infinity, which is the domain of this function, it is defined for all real number values. The behavior is different over subsets of that domain. As a matter of fact, in the part of the domain that is all negative numbers, the activity on the absolute value function is that it behaves like the function y equals negative x everywhere, from negative infinity up to but not including 0. Why not including 0? Because it's not included in the definition that they gave me. And from 0, including 0, to positive infinity, this piecewise defined function acts like the line in the plane and the function analytically, y equals x. So the absolute value function is a piecewise defined function. When you have a piecewise defined function, you need to look at what behavior each piece is exhibiting. And each of those pieces will exhibit that behavior over a portion of the domain. And that's what is listed out here. And I find that that's the part of piecewise defined functions that students really don't understand. But that's telling you over your domain, for what input values does the function act like y1 for these values? For what input values does the function act like y2? Those, whatever they give you. And y3 will be a completely different set of values. We still have to have a function, meaning we still have to be able to pass the vertical line test wherever we draw a vertical line. So we cannot include the same domain values. We couldn't include 0 in both of those pieces, because then we would have two output values for the single input value of 0, and we would fail the vertical line test. So all of these are going to be a subset of the domain of the entire function. Don't let piecewise defined functions confuse you. They're not that confusing. Let's go back to the absolute value function. I'm going to go through this very quickly, but just like all other functions, when we have a translation inside of the function operation, here we have -1 inside of the absolute value marks, so it is affecting the independent variable. It is a horizontal translation, and since it's -1, it's a translation to the right. Same as we've always known. Inside the function operation, horizontal translation, +1, a translation to the left. Remember, we're headed in the left direction, a distance of 1. If it is not inside the function operation, if it is outside of that operation, no matter what the operation is, and it is a plus or a minus, that is a vertical change, a vertical translation. Here it is a translation 4 units down because it's -4. If the negative is in front of the entire function, then it is a reflection saying that all of the positive inputs of that function are now negative inputs. If I distributed that negative, I would have the opposite of this function translated 4 units up in the plane. Everything that we know about all the other functions still holds true analytically and graphically for the absolute value function. Now let's take a look at another piecewise defined function. And I've color-coded things here so you can see what I'm talking about when I'm talking about different pieces of the domain. The domain of this function is again -infinity to +infinity. Looking all along the real number line, all input values are legal for me to put in. I will get a well-defined output if I look at the graph of this function. It just so happens that I've taken the entire real number line and I've taken different pieces of it. From -infinity up to 0, not including 0. And the next piece is from 0, this piece includes 0, up to 1, including 1. And the next piece is everything from 1 to +infinity. That's the entire real number line. But I've broken that domain up into 3 different sets because my function exhibits 3 different function behaviors over its entire domain. For this piece of the domain, from -infinity up to but not including 0, it acts like the function y equals -x. It's a line of slope -1. And on this piece, from 0 up to 1, including 0 and including 1, that includes this point and that point, it acts like the function y equals x squared, but only on that piece. It doesn't act like it anywhere over here or anywhere over here, just on the input values from 0 to 1. On the purple piece here, The domain is from 1 to positive infinity, not including 1. And it acts like the horizontal line, y equals 1. So piecewise defined functions have everything to do with separate behavior over separate pieces of the domain. And once you figure that out, they're not that difficult to deal with. Calculus on them couldn't be easier. Algebra on them couldn't be easier. We're going to practice graphing them, and therefore you should get more comfortable with them. We're going to take a quick look one more time at analytically what we need to know to determine whether we're dealing with a vertical asymptote or whether we're dealing with a hole. We're going to look first at this function. This function, I can factor that denominator. It's the difference of two squares, so I know that factors like that. This function is going to have a vertical asymptote at x equal -3 and at x equal 3. And I know it's going to be a vertical asymptote as opposed to a hole because neither one of those linear factors from the denominator are repeated in the numerator. So I will have vertical asymptotes, and we can see that evidenced on the graph. Now let's look at this function, x plus 3 over x squared minus 9, so the same denominator we were working with on the other function. But this tells me I'm not going to have a vertical asymptote at x equal -3. I'm going to have a hole in the graph. The only vertical asymptote is going to happen at x equal 3 because this linear factor is not repeated in the numerator. Again, look at my graph. What do I have at x equal -3 versus what I have at x equal +3? I don't even need to see the graph in order to be able to tell you that kind of behavior on these functions. Graphically, the graph is the result of what's happening analytically. And oftentimes I find students come to my classroom with that relationship reversed. They think that analytically the function behaves in this way because the graph looks like it does. It is kind of a symbiotic relationship, but understand there is nothing happening on that graph unless the analytics allow it to happen. This is what's in charge of what's going on graphically. Okay? Here's another one. X plus 3 over x squared plus 9. This is the sum of two squares. That does not factor. How do I know it doesn't factor? Because if I set that factor equal to 0 and try to find the x value that makes that a true statement, I'm in trouble. There are no linear factors in the denominator of this function. There's only one factor, and it's a quadratic factor, not a linear factor, because it's to degree 2. This function has no holes and no vertical asymptotes, because the denominator of this fraction will never equal 0. It's impossible. It's impossible to do that and stay in the real realm, and we are in the real realm.